Let's continue taking a closer look at our problem solving agents. So we look at we need to be able to understand and to be able to define problems and solutions. So a problem can be formally defined by 5 components. So we want to understand the basics of designing a problem, but the knowledge can be further extrapolated into real-world problem. So the 5 components that can define a problem: the initial state. That's the first one, number 1. This is the state in which the agent starts in. For example, we want an agent that will drive from town A to town B, so the initial state is the town in which it is. Then a description of possible actions available to the agents given a particular state or states. The actions returns the set of actions that can be executed in that state S. We say that each of these actions is applicable in S. For example, maybe we are faced with 3 different options to move from a particular city. So all the possible cities which we can end before reaching the goal, there are possible actions that we might have to the agent. So that's the second one. It's a description of the possible actions available to the agent. Okay, we might have many. Then the third one is a description of what each action does now. The formal name for this is the transition model. The transition model, it's a name given to try to describe what as the agent transits or moves from one state to another. So it's specified by function result, whereby S is a particular result for an action on a particular S. Like result, it's the action that we can take on a particular state, that is the state that results from doing an action A in a state S. So whatever the action that we do in a particular state, we can go. So we call it a transition. So transition functions are very easy to understand. I think in some certain quite number of computer courses, you understand more about transition function. We also use the term successor to refer to any state reachable from a given state by a single action. So explaining further on the third point, together the initial state actions and transition model implicitly define the state space of the problem, the set of all states reachable from the initial state by any sequence of actions. So it's very important to understand this. The state space now forms a directed network or graph in which the nodes are states and the links between the nodes are action. So you find out, for one to be able to understand this, we need a background of data structures whereby we understand the graph data structure. The graph data structure will just be a pictorial representation of all the states that is linked by the action, and the states will be the nodes. A path in the state space is a sequence of states connected by a sequence of action. For example, we might have a number of states and joined with certain actions. So from particular states through some actions and states, we end up having a path. So the goal test now, that's the fourth component, which determines whether a given state is a goal state. It's very important to check whether, because the idea of a problem solving agent is we want to achieve a goal, so we need to check whether we are in that goal. And a path cost, a function that assigns the numeric cost to each path. For example, if we are trying to make an agent that is going to be drive from city A to city B, it depends with what is the goal. If the goal is to minimize time, then we might assign the numeric cost here as time, or if it's about minimizing distance, we might assign the distance. It depends with what will be assigned on the cost. So those are the 5 items that are used to define what? To define a problem. So a solution to a problem is an action sequence that leads from the initial state to the goal state. Solution quality is measured by the path cost function, as we said, the last component. So an optimal solution is the lowest path cost among all solutions. It depends on what we are going to use to quantify the costs. So, if it's distance, is the lowest distance. If it's time is the lowest time of all. So the problem solving agent below formulates a goal. This one is just a simple pseudocode explaining a problem solving agent, which we described before, but just trying to summarize with a pseudo function. The problem solving agent below, it first formulates a goal and then searches for a sequence of actions that would solve the problem, and then executes the actions one at a time. When this is complete, it formulates another goal and starts over. So this is a simple function to define a problem solving agent, which takes in the percept and returns an action. Amongst the information in the data structures persistent will be sequence, quite a number of the states, goal, and the problem. And these functions, like the update state function, formulate goal, formulate problem, and search, the function, you will understand them, and they will, as you go deeper in understanding the course, and implementation of the function will differ according to the language being used to implement. So a simple example of a chess problem, the 8 queens problem. Here, let's just look at a simple one. The goal of the 8 queens problem is to place 8 queens on a chessboard such that no queen attacks another. We know that queen can attack, as we know from playing chess, can attack horizontally, diagonally, like that. So we want to place the 8 queens on a chessboard such that no queen attack another. So the queen is the right. For example, this diagram which we put here, you find out that the queen in the rightmost column is attacked by the queen at the at the top left. If we sorry, where was the queen? Our diagram was not enough, but there will be a queen down there. So what we're just trying to explain is that as long as you put a queen in the diagonal, it will be attacked by the other one in that diagonal. So we need to formulate some solution. So there are two kinds of formulation. The first one is called an incremental formulation, which involves operators that argument the state description, starting with the empty state of the 8 queens problem. This means that each action adds a queen to the state. The other one starts with all the queens on the board. It's called a complete state formulation, and moves them around. In either case, the path cost is of no interest because only the final state counts. So explaining, let's say we choose the incremental formulation method of this chess problem. The incremental formulation goes by this. The states is any arrangement of 0 to 8 queens on the board is a state. The initial state, no queens on the board, as we said, we have to incremental and checking if they are not attacking each other. The actions add a queen to any empty square. Transition model returns the board with a queen added to the specified square. This is the transition model. We explained this. We just did explaining on problem formulation. Then the goal test is if 8 queens are on the board and none attack. Because the goal is to put 8 queens without attacking each other. So in this formulation now, if we look at the possible squares where the states can be, look how big is the number. In formulation, we've got this 64, approximately 1.8 times 1.8 times 10 to the power 14 possible sequences. It's quite a number of possible sequences to investigate. If we do our permutation and combination, it's a mathematical way to try to check possible sequences. So a better formulation would prohibit placing a queen in any square that is already attacked. So the states are all possible arrangement of n queens in 0 to 8, 1 per column. Now we are dealing with column, trying to minimize our possible sequences in most leftmost n columns with no queens attacking each other. The actions, these will be the states, right? So the actions add a queen to any square in the leftmost empty column such that it is not attacked by any other queen. Because we already know that if we put a queen in any column, it will attack. So we start with the next column and move the chess piece, the queen, to check if there is no, then we place it and we continue. The formulation, this kind of formulation reduces the 8 queen state space from that exponential figure to just 2057, and solutions are easy to find. So the basic idea when you formulate a problem is you need to come up with states whereby you possibly that will make it easier for you to formulate what is solution. And I think we've covered a lot for this moment, and tune in the next. Thank you.